I am Ravinder, lecturer in physics, Extra Government Degree College, Kottagudam. I will be taking a class for BSc first sem, MPC, MPCS. My topic is mechanics. Under mechanics, we have 4 units: vector analysis, mechanics of particles, central forces, rigid bodies, and special theory of relativity. Now, this consists of 4 units, and 4 units gives the same equal marks. The paper for which I am taking consists of 80 marks and 20 marks for internal assessment. Vector analysis. What is vector analysis? What is vector analysis? Definition of vector analysis. I'll give the basic introduction. Vector analysis is a technique to solve 2- and 3-dimensional problems in few branches of physics, namely mechanics, electrodynamics, and fluid dynamics. Using this concept, the relationship among different physical quantities can be represented. Physical quantities can be understood by application of vector analysis. The vector analysis is developed by several scientists to understand the physics in deep. First, we want to define what is a differential operator phi. The differential operator phi is called as a differential operator or operator del. Del nabla or is a differential operator. It is assumed to be having the characteristic of vector. In Cartesian coordinates, del is equal to I dou by dou x plus rho dou by dou y plus k dou by dou z. Grad phi is equal to I dou phi by dou x plus j dou phi by dou phi plus k dou phi by dou z. This is known as del phi, which is a vector. Now, what are scalar and vector fields? We'll briefly define it and give some example. If a physical quantity is continuous function of position of a point in a region of space or represented as a point function, then this region of space is known as scalar field or vector field, depending upon the physical quantity of the vector field. Once again, I repeat, if a physical quantity is continuous function of position of a point in a region of space represented by a point function, then the region of space is known as scalar or vector field, depending upon the physical quantity is a scalar or vector. Example, scalar field. Examples for scalar fields are electric potential, gravitational potential, thermodynamic potential. Examples of vector fields are magnetic induction, electric field intensity. Now, basically, we define what is exactly a scalar field. The point function represents a scalar physical quantity, or if a point function is assigned a scalar physical quantity, then the function can produce a scalar field with a range of variables. Example, gravitational potential is a scalar quantity which is continuous over a range producing a scalar field. Similarly, electrostatic potential, magnetostatic potential, and temperature or function which could produce scalar quantity. Graphically, a scalar field can be represented by the scalar surfaces. Can be represented by scalar quantity. Now we define vector field. If a point function is assigned or represents a physical quantity, then it will represent a vector field over a range of values. Example, in a gravitation field, the field intensity of the vector position produces a vector field over a range of values. Similarly, electric field, magnetic field also produce a vector field with respect to intensity. While moving from one point to another vector field, the vector quantity changes in magnitude as well in direction. Connecting the different points in vector field with the line results a vector line. Every vector field represented by these 3 vector lines. In some cases, they can also be called as streams, streamlines, or flux lines. The quantity flux is number of lines crossing unit area in a vector field normal to the direction of the surface. Flux lines will not intersect with each other. Therefore, for a vector point function, the value is same at every point. The del operator is operated on a scalar and a vector field in 3 different ways. If a del operator is operated on a scalar and vector field, we can define as gradient, divergence, and curl. When a del operator is operated on a scalar field, the resultant operation is called a gradient. For example, if phi is a scalar field, then del phi is called gradient of phi, grad phi. Grad phi is a scalar, then del phi is a vector. Divergence. 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 When a del operator is operated on a when a del operator is operated with when a del operator is operated on a vector is operated on a vector is operated on a vector or the dot product of del with a vector field is called the divergence of a vector field. If A vector is a vector field, then its divergence is called del dot A. Though A is a physical vector quantity, its divergence is scalar. Third definition, the curl, the cross product or vector product del operator with a vector field is known as curl of the vector field. If the vector field is defined as curl of A, then it is called curl A. The gradient of a scalar product. Today in our class, we'll slowly define or use the physical significance of the gradient of a scalar field. So we are considered in the video we are seeing in my lecture, we having operating an operator on a scalar field results in a gradient, and gradient of a scalar field gives the maximum rate of field at that point. The gradient means maximum rate of change of the field at that point. So in the figure, we consider two equipotential surface S1, S2 in a gravitational field as shown in the figure. The scalar values of the surface are S and S plus ds. The change in scalar value is ds. The change in scalar value is ds. By assuming the path A to B, the position vector of the path is given by dr, where r is the position vector drawn from origin to a point A in the field. R plus dr is the position vector drawn from the origin O to a point B in the field over another equipotential surface, which can be shown in the above figure. From the figure, we show that the distance between OA vector is called R, OB vector is called R plus dr, AB is nothing but dr. Now we have to calculate the least distance between S1 and S2, which is in the figure, from the figure which is AC. This is a normal line drawn from the equipotential surface S1 to S2. The direction of AC is along n hat, a unit normal vector. The length of the AC is dn. The rate of change of S at n is dou S by dou n. Change in S is ds is called dou S by dou n into dn. Dou S by dou n into dn. Change in S is ds is equal to dou S by dou n into d. From the figure 1.1, ds is nothing but, therefore ds is nothing but dou S by dou n into dr cos theta, where dou n is nothing but dou r cos theta. Or we can write it as ds is equal to dou S by dou n into n hat dot dr, where n is unit normal vector. Dou S by dou n into n hat represents the maximum rate of change at A along the direction of AC. This vector quantity is called gradient. Grad S is nothing but is equal to dou S by dou n into n hat, or del S is equal to dou S by dou n into n hat. Therefore, the gradient of a scalar quantity is a vector quantity. Therefore, once again I repeat, the gradient of the scalar quantity is a vector quantity. From this, we can tell that gradient of a scalar quantity or scalar field, gradient of a scalar field is a vector whose magnitude is equal to maximum rate of change and direction is along the normal down to the surface. Gradient is independent of reference frame and gradient is invariant. Grad S dot R is equal to dou S by dou n into n hat into dr, which is equal to dou S by dou n into dr cos theta, is equal to dou s by dou n into dou s by dou n, dou s by dou n into dn. But in Cartesian coordinates, the scalar function s is a function of x, y, z. It is a three coordinates. So therefore, ds is equal to dou s by dou x into dx, dou s by dou y into dy, plus dou s by dou z into dz. Grad s dot dr is nothing but dou s by dou x into dx, dou s by dou y into dy, plus dou s by dou z into dz, which is nothing but a dot product of del into radius vector. I dou by dou x plus j dou by dou y plus k dou by dou z, bracket close, dot I dx plus j dy plus k dz is nothing but del s dot dr. Therefore, grad s is nothing but I dou s by dou x plus j dou by dou y plus k dou by dou z. K dou by dou z. Physical significance. What is the physical significance? We have to show by these two paths between A and B. We are taking 2 points A and B in a vector path in a vector field. Yeah, A to B is path 1, B to A is path 2. Vector field can be obtained by the gradient of the scalar field. Such fields are called lamellar fields. What are lamellar fields? The gradient of a scalar fields, which is represented by laminar fields. Laminar fields, an example of laminar fields is electrostatic field intensity, which is given by E electric field is nothing but negative gradient of scalar potential function V. E is equal to minus del V or grad V. E is equal to negative of grad V, where V is a scalar potential function. Gradient of a gravitational potential gives gravitational field intensity. In a laminar field, we want to discuss it particular to laminar field. In a laminar field, the line integral value of a closed surface is equal to 0. Then we can prove that if del S is a vector derived from a scalar function, yes, del S is equal to grad S is equal to del S. If in a vector field del S, imagine the path between two A and B points is shown in figure 1.2. Theta is the angle between the elements of dl and del S. Del S cos theta dot dl is nothing but del dot dl, which is a dot product. Radial vector r drawn from the origin is along the path. Then dl is equal to dl is equal to r dot r plus dr minus r is equal to dr. Del s dot dl is equal to del s dot dr. So del s is nothing but gradient s. Del s is nothing but gradient s. The line integral from point A to point B, del s dot dl, which has limits from A to B, is equal to line integral A to B grad s into dr is equal to A to B integral ds is nothing but SB minus SA. SB minus SA is nothing but integral of ds over the limits A to B. SB, SA are values of field at points A and A comma B. The line integral value from point B to A is given by line integral limit, which has limits A to B. Del s dot dl is nothing but line integral ds is equal to SA minus SB. So in a laminar field, the del s dot dl is 0. This, if it is called, it is 0. The symbol involving the integral over a circle represents the closed integral. Therefore, grad s dot lr is 0. In laminar field, the line integral value of a path is independent of the path closed between on its end values. Therefore, line integral value over a closed surface is equal to 0 in a laminar field. That is known as laminar field. Next, we discuss briefly about divergence of a vector field. Divergence of a vector field. or divergence of a vector field. The divergence of vector field at any point is defined as amount of flux per unit volume diverging from that point. Once again, we define divergence of vector field as amount